I'm Xiaomini. I'm a faculty member in the ECE department. It's our great honor to welcome Dr. Gerhard Fatweiss from TU Dresden, Germany, to give us a talk about the latest advance in communication area. So Dr. Fatweiss has been the Vodafone Chair Professor at the TU Dresden since 1994. For myself, I'm really not an expert in the communication area, but expert in working in this area told me that Dr. Fatweiss is truly one of the few people that has one of the few visionists in this area. He has the unique talent to combine implementation and theory, and he is also a very active entrepreneur. And he has started several very successful startup companies. Dr. Fatweiss has received many awards to acknowledge his contribution to this area. Among those awards, he is IEEE Fellow. He is also a member of the Germany National Academy of Science, and he has studied 10 startups, and also he has managed a very large team. He has been able to attract a great team of talent working for him on the very hard communication problems. I can tell you a little bit of my personal experience. Even though I just know Dr. Fatweiss since last night, I had the honor to have dinner with Dr. Fatweiss. So just for 5 minutes talk with him, I really have an enlightening moment that I can see what's the direction of the communication area is going, even though I know very little about this area before that. So I believe after today's talk, his talk will also give you such experience as I had last night. So without further ado, let's welcome Dr. Fatweiss.
So thank you very much for this wonderful introduction. It's a pleasure to be here. It's my first time to visit Delaware, as far as I remember. I might have passed through the state of Delaware before, don't take me wrong, on one of my trips. But I did not really visit this nice little state, Delaware, so far, even though it plays such a big, important role in US economy, since many companies are incorporated here, as I know. So what I want to talk about today is give you a little bit of an idea of how I typically work and give you some challenges and some future prospects of what's going to be happening to us in the next 30 years. Not 5 years, not 10 years, I think 30 years. Which is obviously, for me, being a faculty, being a professor, having grad students, I always say I have to come up with the challenges such that I know there's enough research to be done, not in my lifetime, but also enough research to be done at least for the first couple decades of my grad students, so that I know they're going to be doing something that is useful. Otherwise, I'm not going to be very comfortable just teaching something that is then not going to be so useful. Anyhow, so let's take this one step at a time. I'll talk about something which we coined the tactile internet a couple years ago. But before I do that, just give you a quick intro. How do we work? This is just my team, myself. I'm one professor, yes, we're a team of about 70 people, plus the students. So my personal team is around 100 people. That is quite large, yes, of which, however, quite a few are managing some of the centers. You see, on the funding level, we put together €500 million in projects, which is a large number also in Germany, not only in the US. And this is obviously not funding only for my own grad students, but for many big programs that we've been able to put together. I copycatted one thing during my time that I lived in the Bay Area before moving to Germany. I saw that you can ask companies to give you funding, no strings attached, called sponsoring. And so I collect sponsoring from the companies up there, and then we have a bunch of project partners. Now, just as I mentioned, one of my missions and visions was when I moved to Dresden, which was 21 years ago. Dresden was basically in shambles. The buildings were all black. You still saw the bomb shelling of World War II. It had just been freed as part of the Western world. Up to then, it was basically communist world. And you had a bunch of smart people, and you had a university that had just kicked out everybody, all the faculty a year before, because they wanted to screen them for security reasons, to make sure that they're not all Stasi. And then we're rehiring the whole new bunch in. So the university got a reset button, and I said, if I can somehow help place this university on the mark somewhere on the radar screen in the world map, then this is something to be doing, more fun than just joining yet another startup or whatever in the Silicon Valley. Maybe I can sort of experience this, and that's why I moved to Germany, to Dresden, a very dirty, run-down city 21 years ago, which is now completely different. Yes, now it's beautiful. So because of that, I put together centers over the years. Currently, I'm running these 4 centers. The one is the German Science Council Center, which I had to put together, or which I felt like I should put together to make TU Dresden one of the top universities. There was this excellence initiative in Germany. In Germany, everything is thorough. So there was a thorough process of defining who are the top universities, with all kinds of outside experts flying into Germany, screening our research, and we had to put center proposals together. And this is the Center for Advancing Electronics Dresden that I put together with 60 faculty from mathematics, physics, chemistry, biology, material sciences, mechanical engineering, electrical engineering, computer science, working on what can we do in electronics beyond CMOS. So bio-inspired computing, new materials, whatever all. Then I put together another center, the German Science Foundation Center, which is currently the only German Science Foundation Center in electrical engineering. By the way, the top left is also the only cluster of excellence in electrical engineering in Germany. So we have 2 of these as only EE faculty in Germany. And then we have a 5G Lab Germany. I'll talk a little about that. And then I have a center that is a twin lab between Masdar Institute in Abu Dhabi and TU Dresden. Masdar Institute is sort of a satellite of MIT, sitting in Abu Dhabi. And since Abu Dhabi has invested $10 billion in Dresden alone, it's the major manufacturing site of GlobalFoundries, and GlobalFoundries is owned by Abu Dhabi. We have put this twin lab together to sort of bridge the gap between these 2 worlds and start doing something. So you see, I'm there in Dresden, having fun as an applied mathematician, as I call myself sometimes, but also trying to do something for the region. And the top left center, German Science Council Center, put us on the map. So now we are one of the 3 only engineering schools that have this elite sticker, that are called an elite university. There's Aachen, Munich, and Dresden only. And if you check out the EE part of it, we are now ranked number 1 according to the Science Council rules for quite some years now in Dresden, even though we had a reset button 21 years ago. And I'm pretty much happy to say that it happened. Doing this on the one hand from trying to build a university or help build a university and a department is the one thing. You never can do things alone. You always have to be a team. The other thing is where you always need to be a team is start companies. So I felt like, okay, if I do this, I also want to see if we cannot help the economy in Dresden a bit. So these are the companies we started so far. So in the meantime, it's 14, if I did the count correctly. So we just founded ComSolid 10 days ago, and we just raised a very nice first round for AirRaise last week, Wednesday, trying to see build something big there in Massive MIMO. And I'll talk a little bit, some of them have seen an exit, and some of you probably have some hardware from us in your hands, or have had it in your hands. Okay, now let's get to the content side. So you see, basically, what I think is important, at least for me, is if you want to work on the equation that is going to sort of be important, try to talk to all kinds of people and try to find out what is the next big step. So I did this in 2003. I sat together. We just had been acquired by Philips Semiconductor. I met the CTO. And the big question was, what is going to be the big step in 2003 in cellular? Is there a future? And I put the wireless roadmap together. And I'll give you just a sneak preview on that. But basically, a nice picture to show what that means is here you see the election of my previous boss, Pope Benedict, yes, at the Via della Conciliazione, and my current boss, the same street, Via della Conciliazione. You see that the world has changed a lot. In the left picture in the bottom, you see two cell phones being held, actually used as communicators. On the right side, you see a ton of cell phones used as cameras. That's it. So now think of these cameras piping all that information into the air, into the network. Then whatever we see in terms of capacity today is not going to cut it. So it is not a question, do we need higher data rates? Yes, we do. The question is, in this area out there, how do we achieve that? So this is what I put down in 2003. I said the data rate is probably going to increase, very simple, Moore's law, doubling every 18 months, which is 10x every 5 years. And interestingly enough, it has happened. So we see that driving data rates obviously is a huge, big challenge. And I could give you a whole talk just about how is it physically possible to have a small device powered, for example, USB dongle powered by 1.8 watts to deliver 1 terabit per second by 2025. So there's a whole bunch of research challenges out of there, right there, thinking of that. And we have to reinvent modulation. We have to look, AD converters are eating everything off the power budget, et cetera, et cetera. So there's a ton of research challenges right there, but I'm not going to be talking about that because that is sort of just the exponential projection. Besides looking at the y-axis going up, yes, the massive content increase, there are some new things happening in the cellular world in the next years to come. And this is what I'm going to be talking about. The one thing, obviously, is massive sensing. You might have heard of LTE Cat-M or narrowband version, a 200 kilohertz band version, where we will be able to connect every flower pot, every sprinkler on the planet into the cellular network. That's going to be a big difference. That's about massive sensing. And the topic that I want to touch today here is the control space. What is it that we have missed so far? I spent, during my last sabbatical 6 years ago, I spent a lot of time thinking and then later on going home to Dresden talking to physiologists and psychologists. What is it that we have been missing so far in human interaction in the network, with the network? And it's about massive control. Yes, so our two newest startups are sitting here. The control part is still empty, but it soon will be filled. So the question is, what is this that is going to be happening? Let's have a look at it. It turns out if we take an object and have a look at it and we move it in front of us, our eyes expect to see a change in the image. And if this image does not happen at the right speed, not at the right latency, yes, of reaction time, then we feel awkward. Which means actually, if we touch and move an object around, what we really want to have is a 1 millisecond reaction time, and then it's real time. That's very interesting, because if you look at your TV screen, everybody said 25 hertz refresh rate is good enough and you see a moving image. That is correct. But if you take a joystick in your hand and start moving that object on the screen, you're going to see the mouse hopping around, you're going to see all kinds of things. Yes, so then the reaction time, if we touch something, the tactile interaction and visual feedback, we want to get down to a millisecond, otherwise it's not real. So if we take current systems, like a 4G system, we have typically 50 millisecond round trip time. We have to get this down to 1 millisecond. Now, obviously 1 millisecond is a challenge because the speed of light is hindering us Why? Because light travels only 300 kilometers, only 200 miles in a millisecond. So if we're talking very far, we know this is not going to work. So that's why the gamers hog these big halls and have these game parties, because they know for their typical reaction time on the network, the online gamers need about a 10 millisecond latency reaction time, otherwise they don't feel real. However, if we put our Oculus or whatever kind of goggles on us, and then we mount cameras onto the system, here you see my colleague Frank Fitzek, yes, and then we could build a system where we can measure, is delay really an issue? Because we wanted to find that out. So we put this together, and now we have basically these cameras. We can project them on the Oculus, and now we can vary the delay. And it turns out, if you talk to people that have done physiological studies, that you need this to be 1 millisecond, otherwise you get sick to your stomach. Yes, and I was just talking earlier in the office here that, yes, you can get any student to be really sick to their stomach by increasing the latency between your head movement and what you see on your virtual reality goggles. It's called cyber sickness. But is that it only? And the interesting part is we start an experiment, so like this, just catching a ball. And you see, that's not me, but the person is catching the ball with the whole body. Now we cranked up the latency to 150 milliseconds. And what happens at 150 milliseconds is this, yes? And now we cranked it down to the lowest latency, which in our setup is 5 milliseconds. And what you see, pretty much a displacement of 5 centimeters, 2 inches between what the person has done and where the ball is finally caught. Because if you do the physics, if you throw a ball, it's about a centimeter per millisecond is the speed of a ball that you throw, which tells you exactly that, yes, even though we have a 25 hertz frame rate, in the video that we are watching and we are completely immersed and our brain does all the interpolation and thinks this is a moving image, if we really start a tactile interaction, a haptic interaction or tactile visual interaction with our real world, we have to get this down to 1 millisecond. So the question is that important or is that not important? Obviously, I think it's going to change our educational system big time. Because, I mean, this is basically how I spend my time in the school, yes, sleeping on the last bench, I must confess. But if we were able to change this, what is the problem if we learn a language these days? We learn a language like an Excel sheet. Left column, right column, and try to memorize in which line which 2 words were, so that you can know what is Latin, what is English, what is Latin, what is English in a translated form. This is not how you as a kid learn a language. As a child, you walk to the refrigerator, you open the refrigerator, you see the refrigerator, you feel the refrigerator, you feel that it's cold air coming out, you have this funny smell of a refrigerator, and your parents tell you, you open the refrigerator, or stay out of the refrigerator. And then you start correlating all these different senses, and that is where our brain has this multi-correlation function, such that we can then remember this much more easily. So if we have a context-driven learning experience with multi-sensorial input, that is when we learn quickly, up to 10 times more, 10 times faster. So if we were to go to a virtual reality and would have goggles on, we move into the old Rome and we have a pickup system that sort of picks up what we're speaking, and we find out, is this correct Latin? And then we get points. If we make mistakes, we get not so many points. Then we start talking to each other in this, and then it starts becoming a very nice interactive kind of scene. And then we can take this to mathematics, physics, all kinds of other areas, and have a complete different learning experience by having this real interaction, real life interaction. For this, we need this millisecond round trip latency. If we take it to another step, to entertainment, where we also need this millisecond round trip latency. We've been to concerts. We hold up, if you're a dad like I am, you'd go to the performance of your kids, and you don't see your kids anymore because all the people in front of you hold their iPads up to film everybody. And if you're not the first one to arrive, which I'm seldom am, I confess, then you get a backseat row and you see nothing anymore. So, but let's look at it. I hold up this camera, what can I do? I can have a fantastic camera. It can be more and more megapixels. Maybe sometimes it's going to be gigapixel. What can I do? I can do zoom, I can do mechanical zoom, optical zoom, I can do electronic zoom. But what I really should be seeing is that to the left, there's a second camera. So if I connected these two cameras, as a signal processing guy, it's easy to know that between these 2 points, I can do any kind of linear interpolation. So I can pan between these two camera positions. They only need to be connected via a wireless interface and have a big rendering engine, that box sitting down there, to do all the computations and provide this, and then suddenly I have a complete different experience. I can take this into a stadium, and then I have 80,000 cameras sitting there waiting to feed me so that the guy that is my favorite player, that I want to be pictured into my goggles, does not have to carry a GoPro. All you need is a little bit of digital signal processing, a massive amount of digital signal processing, and then we can calculate the point of view from this person. And if we all have microphones, 80,000 microphones, we can then pick up his breathing and panting and whatever all, and it's just all displayed into us. And we see the red guy that is just kicking the ball in front of him. And if we say that's too slow, we select the ball and we're hammered at 200 kilometers per hour over the field. This is a complete different level of interactivity. Yes, so if you look at it, when I was a little kid, there was Formula One car racing around already. It was so boring on TV. All you saw was boom, right? I mean, that is as stupid as can be. But now that they have head-mounted cameras or car-mounted cameras, the level of interactivity is way bigger. Or if you ever have watched downhill mountain biking, with these head-mounted cameras turned on, even I get sweaty hands just watching it because you're so much immersed in what's happening. Obviously here, it's not only about latency, but in this case, we also need massive synchronization because, as you know, in a stadium, what you need, of course, it has to be a group experience. We all like the La Ola wave, right, where everybody goes up like this and down again in a big wave marching once around the stadium. If you do the physics of that, you need 27 people to kickstart a La Ola wave. Yes, this is what you can do a theoretical modeling of this. A friend of mine has published this in Nature. So basically, it's also about synchronizing all these terminals down to the millisecond to make sure that you can do this. And here you see an experiment where we can synchronize. Basically, here you see still a lag, a latency in this whole thing, but they're really synchronized nicely. And we can take this to 120 tablets that are in our lab and actually show you with network coding that this can be synchronized. So there's a lot to be happening in edutainment. Now let's move one step further to robotics, where again we need this 1 millisecond tactile internet. If we want to clean up a hazardous situation, what do? We move in with these kind of robots. If you have ever tried to take a remote control and move one of these robots, it's scary. Yes, I mean, it's really scary. So I rented a little excavator once, a little bulldozer, because I wanted to get new pipes to my house, and I nearly tore down my house by just trying to move this little mini thing there, and quickly hired a person that knows how to use this. So it takes months to learn how to use this kind of a thing. However, if we were to use a humanoid robot that would walk into that kind of situation, we put our goggles on, and the humanoid robot just mimics, copies what movements we have. Then we can extend our current presence into this real other presence and capture what is being done. And why is it important to be short latency? Because something drops, you want to catch it. And there again, we need this very short latency of reaction time, where we need the end-to-end 1 millisecond latency. If we then move this with even haptic feedback, you can see here a chair that we have in our lab, in our department downstairs. And so here we can really do experiments with haptic feedback, and it turns out that physiologists tell you need, and psychologists, you need 1 millisecond haptic feedback. So a tactile haptic visual feedback system is all on the order of a millisecond. If you move your finger here over this crevice, and it should feel as if we're going X, whichever direction, it should feel the same. I have to have the millisecond. In this case, you saw the guy did not lose this very loose plastic thing. It felt like a piece of metal, even though it was just this hollow structure, because we have this 1 millisecond haptic feedback control. So if we take this now to robotics, where it is being used widely, which is industrial robotics, the question is, how can robotics drive this? And here you see basically robotics with its newest products is actually getting exactly to this human speed. This is the KUKA Agilus playing against the world champion in ping pong, and there he loses out, yes. And it's a whole long video on the web that you can watch. In the end, yes, T-Mobile also won a couple points, and not only the robot, but it shows you that we are there to get these kind of reaction speeds from the robots, but now we have to get the communications right to control these robots. Today we do this with cables, but we have to get mobile. Why do I have to get mobile? If you look at the factory here, one of the biggest challenges is getting all those data cables to the endpoints of the robot arm. Power is just 2 cables, right? But all these data cables is a big challenge. You have these small data cables, the robot is wiggling the whole time, and these cables tear and wear. So it's a big challenge making sure that you replace the cables on time so that manufacturing is not hampered. So that's number 1 why you want it wireless. Number 2 is, what do we see here? We see copy-paste of the same product. That's not individualized manufacturing. That's Henry Ford. You can build any product. You can order any car, my car in any color, as long as it's black, is what he said, right, initially. So it is nothing about individualization. And since we have gone to mass manufacturing today, this means we have a big challenge. We want to go back to individualized manufacturing. Now, let's look at the controls of this robot. The robot has an arm that's about 3 meters length. Resonance frequency is 100 hertz. It's a not pure second order system, so controls tells us we sample 10 times per period and counter any resonance frequency, and this is what the whole industrial controls is about. So if you go into industrial controls, the spec is always 1 millisecond end-to-end latency, always, to make sure that you don't have a resonance buildup and crash the cars. So if we want to go to an assembly station with individualized manufacturing, we have robots whizzing on the ceiling, on the floor, that need wirelessly to be controlled. And then we can build any product at a very cheap cost, individualized to what you want to do. And for me, this is important when I talk to politicians, yes, so, which I do once in a while, to try to give them, of course, get more funding, that's clear, and to wake them up. So that means actually with this kind of an idea, we are going to generate a ton of jobs. We're not destroying jobs, we're generating a ton of jobs. Why? I go now to a shopping mall. I don't only have big department stores and boutiques, but I have design stores as well. I go in there, I look at my virtual mirror. I don't see what I have on, but I have a projection of that. And I can choose this, and I need help because I don't want to look stupid in the end and just base my choice of clothing on what I myself have done. So I want to make sure that I have an artistic minded designer sitting next to me, standing next to me, helping me out. A ton of new jobs for the artistic minded. And then we need obviously the latency to be correct, because otherwise if the latency is not incorrect, here you see the virtual mirror in action, it's somehow interesting to see what you see, but it's not necessarily what you want to sort of base your decision upon and choosing this or that kind of design and fabric. Okay, so for this again, what do we need? We need this whole new concept of a millisecond end-to-end. Now the question is, besides industrial manufacturing, is there something else that has a millisecond today? Yes, there is. Again, the wheels of a car are about 3 meters apart. Again, we talk about 50 hertz or 100 hertz resonance buildup in a car. And there we again have gravel and all kinds of dirt and whatever all underground. So it's a nonlinear impaired second order system. So in the case, again, all the electronic stability control is about an end-to-end latency of 1 to 2 milliseconds. So this is what we know, what we have in our cars today. Tomorrow we want to go to platoons of cars and want to have autonomous driving of cars. Now everybody in the industry, not necessarily in public, but many people in the industry know that autonomous driving is a nice concept, but it doesn't really work. What's the challenge? So if I am in a traffic on a freeway and I'm the second car in a row, what do? I keep a distance to the car in front of me, and this car in front of me is a second order system. It accelerates, decelerates, accelerates, decelerates the whole time to sort of keep a common pace. Speed is about the same. And I do the same. Try to keep sort of the distance the same. And the car behind me is doing the same. Now, if the cars move too closely to each other, these are not independent second order systems anymore, they become coupled. And as we know from chaos theory, and already 100 years ago from physics, if I couple more than 3 second order systems, I get a chaotic buildup, and it's an uncontrollable system if I have individual controls. So then I have to actually control these things together. So what does that mean? That means autonomous driving works very well in light traffic, fluffy traffic, but we really wanted to deal with heavy traffic. In those cases, it doesn't work. Yes, and so then we need all these elements to communicate with each other. Either we have the master up front, which is maybe a Peugeot, and then we have the Porsche and Merc following the Peugeot, and they follow what the master is telling us, which is maybe not so cool in terms of the way you can convince a Porsche designer to design their car. And also the number of communications that we need is way too high. So what we need basically is a cellular infrastructure, some kind of an infrastructure that we can rely on being there. We can dock into this kind of a platoon, and we can get out of this platoon or convoy as needed as us. And then autonomous driving with these kind of platoons and situations as we wanted actually work. We said, okay, we were pointed out by Bosch that this problem existed, and then a couple years ago, and then about a year ago, we put this experiment together. We took Lego Mindstorm, ninth grade students from school, and asked them just to put this together, and they follow this black line. They keep a constant distance, and you see it's a decoupled system. Everything is fine. So the question is now, how do we get the coupling in there, or how do we experiment this? So what we did is we just put in the disruptive element, not the door, but you'll see the cardboard box. So the first one stops, we see everything is fine. The second one stops, the third one stops, just as theory tells us. And the fourth one is the one that gives us trouble, just as theory tells us. And now the first and second are starting to wiggle as well. Now this is not necessarily what you want to have happening on a freeway. So good luck to your autonomous driving Tesla, or whatever you have, yes? This is not what we want, so we need a centralized controlling instance to keep that under control. If we do that, we can get rid of traffic lights, obviously. The cars can whiz over intersections. The person that is crossing the road just turns on his cell phone, has its personal bubble turned on, and everything is fine. Nobody is hit, and even every frog that gets a little implant can cross the road without being hurt. And if you say, this is crazy, well, let us take us, obviously we couldn't do this experiment in Germany because that would be illegal, but here you see a normal intersection. Now we turn on the tactile internet, and you see everything is completely fine. The efficiency is now 10x higher. Yes, you see the platoons of cars. Yes, we had to choose identical cars of platoons. But even the police that is coming now here on the bottom right actually acts correctly and nicely goes into this. And myself, I'm coming now here on the left-hand side with my backpack on, as you know me. And I cross the street and I'm still standing here. You see, I mean, that's way more traffic being carried by that intersection. And it was a little oozy at this point right here, yes, if you check it out. But as you might know, this is Fernando Lifshitz. This is from BS Films. This is just an artist creation. This is not real life. But it pretty much shows the way the future might be. Then, if we take this to a next level of robotics, where do we have plenty of robotic equipment in place today? Probably much more than in factories is in agriculture. So what do we want to do? The harvesters of the future and the agricultural system of the future, they're pretty high-tech things. So what is the big challenge of a harvester? The harvester goes through a field and it doesn't know what's in front of him except like the corn. But the noise level is 92 dBA. And if you ever have been in a cornfield and the harvester comes towards you, you have no clue from which direction it comes because of the echoing of the different corn and the low frequency. You have no directivity. So that's why it's a problem, challenge, to make sure that you detect what is happening in front of you with flying drones. You have to connect the decommissioning truck that is driving next to you to exactly be positioned at the right point. And it turns out that this is one of the big challenges in harvesting, in productivity increase, is to make sure that all this is fully automated. You have drones flying up front in future doing radio imaging of what's happening in front of you, so don't pick up a deer and contaminate your harvest goods. And in Germany, actually, the big problem is bicycles in the fields because people steal bicycles and then decommission them in the fields because it's so easy to hide them there. And that is also going to hurt the equipment. So we can increase the productivity big times by putting wireless enabled controls at this 1 millisecond tactile interactive speeds. And here we work with Claas, which is, by the way, the second largest behind John Deere. Okay, so let's summarize. What is the revolution we have had so far? We've gone from a revolution of cordless telephony to cellular telephony. What is the big step? Both is wireless. It turns out there's a huge difference between cordless and cellular, and the biggest difference is not that I have coverage, but the person I want to call has coverage. Yeah, I can have every payphone, and there were plenty of payphones in the US, if you remember, in the good old days. If they were all cordless base stations, I could equip this system to have nice enough coverage so that if I want to initiate a call, I just go to the window, I just go close to the payphone and I initiate a call. But how do I tell the other person to move their body such that they have coverage so that I can talk to them? So the ubiquitous access of the both ends is the cool thing about cellular. And we'll see this with the Internet of Things happening in future. So we see that this is basically what we have seen, GSM, yes? Do you recognize that person? I have a new picture of her right there. Yes, well, then we went to 3G, and now we're at 4G, and people are talking about car-to-car communication, whatever, all, but only for information display. So if we look at our current system, what do? We move content from A to B. That's it. It's fantastic, don't get me wrong, but that's it. What I talked about is actually starting the same revolution in this area, which is remote controls. Yeah? Today, it's a point-to-point solution, like the cordless phone. And for us, this is completely natural. Just as was 20 years ago, 25 years ago, completely natural cordless phones are good enough. Who needs cellular? But if I was able to fly a robot, fly an infrastructure, something based on an infrastructure being there, having ubiquitous steering and control communications available, then that will be a revolution. And the number of applications that pop are just humongous. And the nice news is the number of challenges, technical challenges, are also humongous. And the best news of both is that, and this is a slide I specifically had to design for executive board meetings with big multinational boards, where they asked me, what is the business case behind this? Okay, so I had to go and do like a DataQuest analysis, similar to DataQuest, and look at this. And how do you do this kind of analysis? As an engineer, you just find out and then carry out the same thing. You take a country, you pick a country, and calculate the total addressable market, TAM, the TAM, in a market. In this case for a telco operator, because the first board meeting that I attended where I had to present this was for Deutsche Telekom. And so if you take mobility management and provide this as a service, that's at least a 12 billion per year business just for the telco operator. If we then go to manufacturing, this is again at least a 10 billion, and then in events is a 5 billion, edutainment a 10 billion, caretaking a 10 billion or 8 billion, smart grid a 10 billion, and then there are all these emerging new markets that I don't even touch. Then you have to take the GDP of Germany, which is 4.9% of the world's GDP, so my factor in a factor 20. The operator has about 10% of the value chain, so you have to take this times 200, and then you come up with 20 trillion. Now 20 trillion is a step up that the world has not seen so far, because the world today is to 75 trillion. So this would be bigger than anything else that has happened so far. Now, even if I did a 3 dB error somewhere, this is still big. Yes, that's basically the mission that has to be taken here. Now the question is, what are the challenges? Because as researchers, we want to look at challenges. Yes, there's the wireless, the hardware challenge, the network, the internet applications. If we look at these challenges, myself as a physical layer guy, that's nice, but this is not much you can do. So you have to build a team of other professors, and so we build a team of 20 professors to tackle this and have a look at this with more than 500 researchers involved and all these companies funding it. And we've started quite a few companies already, not only my team, but the others as well. 28 companies in total. These are the companies we currently collaborate with, and specifically on this 5G tactile internet, these 8 companies so far, with certainly 2 more to sign up by the end of the year to sponsor our center. Now we've also put together a program, Frank Ellinger and I, to understand what are the different application the requirements. Because obviously if you talk to Siemens Bosch that do industrial controls, it's very different than talking to the Olympic training centers on the top right. That is what these guys are. Yes, because they want to increase the amount of gold medals by synchronizing the paddle stroke in the German teams or others. So we put this big program together, a 75 million program, to just do an analysis of what are the different requirements in different fields. In the end, we have to go from a sensor to an actuator in a millisecond. So what does that mean? That means we have to reinvent everything, because one OFDM symbol, one single bit in LTE is 70 microseconds long. So getting a packet over the air in 100 microseconds is not going to cut it, because a packet in LTE is 1 millisecond long. We have to assemble the packet, we have to transmit it, we have to detect it, we have to error correction, decode it. Forget it. That's 4 to 5 milliseconds right there. So we have to reinvent the wireless part, but also we have to look at this part, because we have the receiver and transmitter and the controller. The controller cannot be sitting in Alaska. It has to be as local as possible. We even think it should be in the same chip. So let's have a look at how such an edge cloud hardware can look like. Edge cloud meaning I have to move my computing to the edge just before the wireless link starts. That's why people call it now edge cloud. So we think actually we have to combine this to come up with a new way of signal processing, which we do here. You see, this is a chip we designed. We published at ISSCC in 2013 with dual PEs. Dual PEs mean that we have one memory and 2 cores hanging off the same memory. A vector DSP doing the demodulation, then we're finished. And then we can have the RISC microcontroller turned on and just take what's in the memory and do the controls. If you want to go off chip to a control chip, try doing it. But you're wasting power, you're wasting latency. So we have to come up with new ways of computer architecture to actually build this. Next thing that we have to think of is the number of cores is increasing. So let's have a look at this new this center that we have, which is just looking at the new computer architecture of the future. If we talk about multi-core systems, we're not talking about 2 cores. 2 cores is easy. We have 1 communication link. 4 cores, we have 6, and so on and so on. And 64 cores, we need 2,000 links to have every core connected with every core in a single hop. So obviously, single hop communication is not going to work. So what does that mean? The challenge of a computer architect of the future is how to design things to keep the data as local as possible, and then build a communication architecture to support the whole thing. Because building a next x86 is not really going to change much. It is the communication fabric and memory management that it makes the difference. So if we look at the printed circuit board with, like, say, 9 chip stacks sitting on there, each and every one is not a chip anymore, but a 3D chip stack with multiple chips stacked on top of each other in future. How do we have communication? So what we do is embedded optical waveguides communicating, and then we have to put this into a backplane, but forget a backplane. Way too low, way too power hungry. It turns out taking millimeter wave at 200 gigahertz carrier frequency gives us the opportunity to have antenna arrays on the top chip and have point-to-point connections and have a fully connected system right there. Sort of a we call it a fat hypertree. And each of those links has to be about 100 gigabit up to 1 terabit per second data rate. And then we come to a solution that is really gigantic. We're being supported, or we're being helped by GlobalFoundries, IBM, and Amazon Web Services in trying to make sure that we're not coming up with something silly, but that we're really seriously looking at these challenges and designing something of the future. What does that mean? That means if we put the numbers together and say we have a board with 4x4 chip stacks, it's double-sided, and we put 4 boards in a box, what is it about? The size is about 10 by 10 by 10 centimeter cube. That's 1 liter volume. So in 1 liter volume, you can fit 1,600 processor chips and 16,000 memory chips. That's 10 to 8 processors. That's a 0.1 exaflop computer, which is as big as the biggest machine on the planet today. And this is sort of just fitting in a liter. And getting this down to 100 watt power consumption level obviously is a big challenge. And this is what we're trying to do. Obviously, it's also a challenge in terms of 10 square meters of silicon. That's another story. But then we can drop it into any car behind the dashboard. We can pack it into any Wi-Fi access point, any base station, whatever. And we have, in today's terms, infinite compute power. That's not infinite, but it seems to, in today's term, infinite compute power to run these control applications. So, and here you see some chips where we basically show that the 200 gigs is actually ready to go. If we get this going, however, it turns out, and we want this tactile internet to happen, it's not only about the edge cloud, it's also about resilience. Because what do we need? For the cars to work correctly and efficiently over an intersection and control such thing, we need an outage of 10 to the minus 5. Now, if we talk about wireless communication, we have multipath. When we have multipath, we have fades, and with fading, we can overcome by boosting the signal power. Then the fade is smaller and smaller, shorter and shorter. We can reduce the outage. But if we want to get 10 to the minus 5, we need about a nuclear power station for every base station on the planet. And we don't only, and we start frying everything as well. So that's not so cool. So the question is, how do we make sure that we get this kind of outage? It's impossible. Wireless always has fading. And we need 10 to the minus 8 for industrial controls. That's 3 seconds a year. What is it what we typically have today? In a very good system, we have 3% outage on a link. 3% outage is 40 minutes plus per day. Now, you don't want to stop your manufacturing 40 plus minutes per day. And you don't want to close down your intersection or say, well, it doesn't matter, but in 40 minutes out of 24 hours, cars will crash into each other. It's not going to be efficient either. So what can we do? And the good news, however, is since this is based on multipath fading, depends upon your carrier frequency. So all you need to do is add a second carrier frequency that fades independently. And there we're at 10 to the minus 3. Second base station, because these base stations also sometimes need to reboot, et cetera, et cetera. So in theory, we can get down to very small outages. And as if you looked at this in the lab, or we did an outdoor measurement, here you see, this is then called coordinated multipoint in cellular, where the access point that is not, the base stations are situated, as you see there, in downtown Dresden, and the VW van is driving along. And you see basically 3 lines here, blue lines and red lines. There are 2 mobiles connected to the VW van. And if we talk to all 3 base stations simultaneously, we have the throughput of the top line, so we can massively increase the throughput in the red case by exactly this kind of building in the resilience by having the diversity. And here you see that in case of Rayleigh fading channels, we can get a massive reduction even. For those that don't know much about the mathematical details, just look at this. That arrow goes down from up there to down there. This is the power that I need to get the purple line. The purple line is 2% out, 10 to the minus 2, so 1% outage. 1% outage, I can get at a certain power level. I can reduce the power level by 10x by using 3 base stations. So each base station uses 1/30th of the power on average. So this does not necessarily need more power. Or I just keep the power and move from 10 to the minus 2 to the red curve 10 to the minus 9. So this is basically what is in this. So I'm here to tell you it is possible to have a cable-like connectivity in wireless, that kind of cable-grade connectivity. Now, obviously, we need to not only think of doing this on a point-to-point link, we have to think in the network, because those routers also fail once in a while. So we have to find new coding methods, network coding methods, to code via multiple links to multiple base stations over the multi-mesh network, and have multiple compute engines sitting there that also fail once in a while, so we need distributed control. That is a challenge. If you want to solve that within the next 5 years, you're pretty smart. That's why I say this is a challenge that is going to keep us busy to get different levels of grade in this year over the next 30 years. And then there's the next problem that we still need to do handoff. Today we do a handoff of one terminal to one base station. Now the whole control server has to be handed off as well. As you're driving along the road, the freeway, what it is, not only does the connectivity have to be handed off, but the whole control server has to be booted in the next base station, has to be run, the state synchronization has to happen, and then the handoff happens. And so you need to program this whole thing. We put this, we're part of this big EU project where we're actually trying to build this kind of control server architecture with all these companies involved to make sure that we can build these kind of things. I just pop over it. And finally, obviously, we need to do a new air interface because we have to be scalable in bandwidth, address all kinds of different bandwidths. We want to have the same clocking scheme as so far. We have to address fragmented spectrum because especially like in countries like India and other countries of the emerging markets, there's very, very little spectrum available, much less than here in America, because they buy military equipment from the US and from Russia, and they are using non-overlapping parts of the spectrum, and so there's very little left over for commercial use. So you need, not only here, but in general, in many big countries on the planet, the way to sort of allocate a fragmented spectrum and have asynchronous spectrum and have a local, very short 100 microsecond packet latency, end-to-end latency over the air. This can be done if we take an OFDM symbol, as it's done today, FFT-based, which means we have in time and in frequency symbols spaced like that, we can make it shorter, but if we make it shorter, we automatically make the symbol wider. What does that mean? For the communication guys among you, that means we get frequency selectivity on the subcarriers. So we transmit an orthogonal signal, and we receive something that's non-orthogonal. And the whole goodies of OFDM are gone, because the whole idea of OFDM is that you receive and transmit orthogonally. So what can we do? OFDM, however, is really cool, because we can add subcarriers as we want. We can take subcarriers away. It's fantastic. So what is the whole idea? Due to the channel dispersive nature, intersymbol interference dispersive nature of the channel, the whole idea is that we make the cyclic prefix, we carbon copy the last part of the signal, of the symbol, to the front, called the cyclic prefix. We carbon copy that there, and that is as long as the time dispersiveness of the channel. By doing that, we can show that we can take out the effect of the channel completely, and we can do basically symbol by symbol signal processing in a very nice way, doing just FFT-based signal processing. So in theory, there's nothing that tells us that we can't do this for a chunk of multi-carrier symbols, but people haven't done it so far. So the idea is not take one symbol and take a cyclic prefix, but take a ton of them. If we do that now, we have something cool. Now, as you count, in this case, we have 8 symbols per carrier. That means we can do filtering on a subcarrier basis, which we cannot do before, because we didn't have enough. We only had one tap. So now we have 8. Now we can do filtering. We can do filtering in a tail biting mode, then take the cyclic prefix, and off we go. Another way of looking at it, OFDM, yes, cyclic prefix, single carrier FDM, that's a single carrier approach, and GFDM is just saying, why take the 2 existing extreme cases and why not meet in the middle? Then we can start filtering with cyclically per subcarrier. When we do this cyclically, we can do this just in the FFT domain and the 2D FFT domain, and then put our cyclic prefix up there. The cool news is, you see here now we suddenly get this very deep notches in our spectrum, so we can do discontinuous spectrum aggregation. So this is basically, you see, the way I like working is trying to see what are the challenges, where are they, how do we find ways of getting around them, and then coming up with ideas like this. Then, obviously, people say, well, filtered subcarrier systems have been around, like FBMC, and the big problem is you cannot do MIMO. Yes, you can do MIMO. You can even outperform OFDM. Now, people say this is ridiculous, and I said this is ridiculous, and I tried to hold back this paper of my students for some time until I understood what's happening. We first had to write another paper to understand before we published this paper. And the reason is very simple. We outperform OFDM by half a dB. So I don't count for cyclic prefixes and whatever, just the OFDM part. It's very simple. If you take a 4x4 signal constellation, we call it 16 QAM. This is the packing that we do in a normal space. Now, due to the filtering, what happens, you can prove this very nicely, that the distance spacing becomes larger, which is equivalent to packing it like this, and that gives exactly the half a dB performance gain. So it is not this, but basically that's sort of to visualize what is happening. And so yeah, here you basically see that we basically can do multi-carrier by having scalability and bandwidth. We can do fragmented spectrum by having these deep notches, which is very important because you have different parts of the spectrum in different countries all over the place, and you don't want to have analog filters for everything. And we can build compact packets with this new air interface model. And this thing basically gives us higher spectral efficiency because we have these deep notches. It's very easy to copy, because it's basically OFDM. We can copy everything that we know from OFDM, copy it over like signal, channel estimation, etc. And it's very small in complexity because we do everything on the FFT based, and it's MIMO ready. So let me get to the conclusion. I try to give you an idea of what I think is important. Important in our research is always not only to work on the coolest mathematical equation on the planet, I love doing that, but important is to put it in a setting such that we're trying to answer the questions that will be coming up and that will be very important in 10, 20 years. So I spent quite some time trying to understand this, talking to many people that have had input here to come up with this vision that the tactile internet is really a big step for mankind. We will build a ubiquitous infrastructure to run controls. And that is not just what we see in the 2G, 4G, or through 2G, 3G, 4G step. That's a big step. It's a new dimension. So then we have an infrastructure not only for content, but also for controls. And there are tons of opportunities, yes, to make money on this. And this is great as well, because I mean, we want to help our grad students make sure that they can start companies and make the world go round. So if you think Facebook, Google, whatever were big, yes, they're big, but they're at least as big of a companies that are bound to be happening soon in the next 10 years with this vision to coming to fruition. And of course, I have to say thank you to the sponsors that sponsor this, and I thank you all for listening and participating in this. Thank you. Do we still take some questions or what?
Yeah. So, questions?
Yes, there's a question right there in the back. Yes. I can repeat your question. Yes, you're right that plenty of the discussions that are happening in cyber-physical systems are a special case of this bigger picture. Yes, absolutely true. What they typically don't cover is this a worldwide ubiquitous access that will enable services that we cannot even think of today. So that's the big difference between having just a robot with wireless controls or a whole infrastructure being able to drive this kind of a system. So what are the biggest challenges? I mean, we're trying to address 6 big challenges. One is the low latency. Then the second thing is resilience, right? I think resilience is a super big challenge. The third is actually end-to-end security, right? Because that is yet another thing. The fourth, where we see some value in what is happening now with this Cat-M or MTC narrowband, how to incorporate all these sensing information pieces into that big picture. Yeah, I mean, that is obviously very, very big. So the next thing is obviously looking at the challenge is how to implement this edge cloud. Yes, because I mean, we don't know. We have some ideas, we have some proposals, but you have to get through the embedded system, operating system, through the protocol stack normally, and that is already a problem on its own. So you have to build tunneling, which is unheard of today, so that the system is ready, the packet is waiting there, and the content is arriving as it is and being packetized and sent out without having to be handled step by step from the ISO OSI stack 6, 5, 4, 3, 2, 1, all the way down. And then still above that on the operating system. So there's plenty of things there. And then obviously, if we package that whole thing together, one of the big challenges is really to understand the trade-off between all these parameters. That is a challenge on its own, because it turns out that, yes, we need 10 to the minus 8 outage in industrial controls. But industrial controls where we need this, we're sending only 1 kilobyte packets, not big camera pictures, whatever. Then we have this entertainment or edutainment applications where we need gigabits per second in terms of data rate, or terabits per second. But if we miss a frame, the world's not going to die. The person's not going to die. Nobody's going to be hurt. So it's not like a big challenge on that side. So we can trade off data rate versus resilience. We can trade off all these different things. So that's why we put this FAST project together, to find out what are the different points in trade-off, so that we don't over-engineer, because that's a challenge on its own. Yes, in Germany, people try to over-engineer things typically, right? They engineer them until they cannot deliver, and then they fake the software. So how do you make sure that you can do this in a way that you can trade that off in the respective way?
Actually, I have a related question, and actually I'm glad you mentioned that. It's about the end-to-end security part.
Yeah.
That you haven't mentioned in the talk.
No.
Could you give more comments on that side?
Yes. So basically, there's a big movement right now. I know of a couple startups that are starting or have started already. If you look at what is being offered by Cadence in their Tensilica tool suite, or by Synopsys in their Arc tool suite, by ARM in their tool suite, of secure boot hardware, software, operating system, to make sure that from a microcontroller point of view, you can have secure end-to-end security systems. We have a bunch of research going on in there. And actually it turns out that what I showed you in terms of network coding actually helps a lot. Because each and every one of these links has maybe only 2/3 of the information. Yes, encrypted and only 2/3. So if you eavesdrop on a link, on a node, you can never reconstruct until you finally hit the endpoint where everything flows together. So it's a combination of many things to make this happen. And this is, if you talk to like the robotics guys of German industry, they're really scared of that, right? To make sure that there will be end-to-end security. How can it secure that can really sign off? Nobody has designed any additional transistors into my chip, any additional software onto the stack, and whatever all. So it's a challenge on then having the security systems there. But I think we're going to get there. Yes?
Through the speech, we know that the low latency and the tactile internet is very useful. But can you introduce what's the progress, of this technique in your lab, and what do you think? Which bottleneck is effective in our common people's life?
Okay, so first of all, the question is, what is the progress that I've seen in our own work so far? Right, that was the question, number one?
What's the progress in your lab?
Yes. So what we have been able to show already in our lab, and have already delivered as just as a demo, is actually a wireless interface system designed in NI USRPs to deliver below 1 millisecond latency. This is not 100 microseconds yet. What we have shown in the lab is to show these waveforms that they really work, that they're real-time demodulated. We've shown in the lab already, you can go in the lab and look at the network coding for resilience. We have demos up and running for security, answering the questions of the previous guy. We have 4 professors, 4 faculty just working on the security issue on itself. So we have demoed a whole bunch of little pieces. And once a year, we have this industry day. We had our big first industry day last September, just this year. For the first time, we just started the lab, the center, a year ago. And we had more than 200 people from industry flying in from all over the planet to visit us and look at that. And we have, in the meantime, we have 12 demos up and running, demoing all kinds of different individual aspects. Nothing integrated yet, but for a center that has started a year ago, that's, I think, pretty good.
Yeah, so we are literally running out of time.